We will have essentially three sections. The first one, I will introduce you some of the basic knowledge about the computer vision stuff. So we will talk about the contour, the convex hull, and we will talk about a feature detector called MSER, and we will also talk about what's behind a face detector. So we will only go over those things very quickly. In the second section, Brian already developed a Jupyter notebook for us. If you do the Git pull, you can see the material there. All the codes has been extracted from the Duckietown repo. Okay, so it will definitely help you to know what's in the repo and how to use them. Okay, so for example, the face and the vehicle, actually the circle patterns, and Ducky and more. Brian will also help us run through the step G, the create a Rust package. So today, if you don't have a Rust package and Rust node yet, you will have it. The last part would be you can play with the starter code. Okay, so for example, we actually buy some fake cockroach. And we already push it into the repo already. So I think that you will be able to use some starter code in order to detect your own targets. You can detect your cockroach. You can detect your parking space. And you can detect something else you want. Okay, so let's get started with the convex hull. Okay, when you see this part, and you see something around it. Today we will only talk about the 2D case because we will only deal with the image in OpenCV. And can anyone tell me what's a convex hull when you see this picture? Suppose let's think about a 2D situation. There are maybe a few one or two definitions. 凸面的壳会有什么特性呢？那有凸面的壳，有没有凹面的壳？可能有哦。好。那我们一起来看好了。This is the first definition. So a region R is convex if and only if for any 2 points, x1, x2, R, the whole line segment x1, x2 defined by its ends points x1, x2 is inside the region R. Maybe if we draw something, that will make it easier, right? So okay, let's take a look. Suppose this is R, and we have x1 and x2 over here, and every single point in the whole line segment is inside the region. Okay, so this is a convex. Let's take a look at another example. Then how about this? This is not a convex. Okay. So from this example, actually there is another definition for a convex hull. So can anyone think of that? Okay, I know what is a convex hull and what kind of property the convex hull will have. Actually, the other definition is more like a rubber band. So it's about the area, the smallest area. So you can see that suppose you have a rubber band and you put the rubber band around this region, and the rubber band should fit close to each of the edges. 那刚才有提到是凸面的，对不对？那其实就应该就有些情况，例如说它不是 convex hull， 它就会有凹进去的部分。Okay. Okay, so this is called the concave parts of the region. So we can see, well, here C1 and C2. So we will jump to the concave, the tree over here. So you suppose we have a region S, and there are some concave parts in this region, and we can actually decompose the whole region into several different concave regions. And we can also build a tree for it. So far, you may be curious that how can we use a convex hull in our application. There are some applications for a convex hull. The first is called the shape representation. For example, if you have a symbol, character, for example, so people try to, when people want to do OCR or do text detection, they may use the convex hull to see how many concave parts inside. For example, a B, you will see that, okay, there are two, maybe more than two concave parts in this region. But for an O, there will be only one concave parts, for example. Okay, and some pattern recognition or also some application in 3D. So the typical case would be that the one of the shape people run the convex hull application algorithm, and then it will become one of the feature for that character. Okay, and this is what we have for Duckietown. Detecting a ducky and make sure the ducky is safe is extremely important in Duckietown, right? So you guys already know how to do HSV, right? And then you can do the in range so that you can get a threshold image, right? And in this case, you can also just do something simple for a ducky. Okay, and you can also use a convex hull to maybe to circle around this ducky. And you can, so far maybe just for color, it's not that robust, right? So you may think that suppose there are some yellow lines on the ground, the ducky will be confused between with the lines. Okay, so that in that case, if you have the convex hull, then maybe you can also, the ducky is actually, you can find some, maybe some ratio to detect a ducky. And even better, you can also detect a ducky. It's that the ducky at the front, or ducky at the back, or even from the side. Right? Maybe this will be useful in some scenario. So now let's move on to the second detector we want to introduce for today. And this is actually one of my favorite feature detector all time, because I have been doing something like text detection for my research, and this is one of the best way to do it. Okay, so you can see that suppose you have a mark with Harvard University, and you want to detect some of the regions, right? Okay, and this is how MSER can help us. This is one of the example. We try to use our moving camera to see the world, okay? And you can imagine that because the autofocus blur, or maybe motion blur, because the camera is moving, right? And the image is definitely not like a scan image, not like the OCR. You know where it is, right? And then you can scan it maybe by your phone, and you can get a high resolution, very sharp image. But this is typically not the case for any moving camera. You can imagine that suppose we use a grayscale, and we have the value from 0 to 255, and the image will look like the right-hand side over here, more like a landscape somehow. Okay, and MSER, the algorithm is actually, this is one of the analogy here. So you just have the water from the bottom, and it will increase on the grade level. And later on, you will see that the region will be filled more and more. And this is essentially the algorithm for MSER. Okay. Then let me show you a better example over here. So maybe from the top, you can think of that the water level. If you just have maybe the water level at 30, you will only see something at the bottom. Okay, and if you increase a little bit more, the B will become thicker, right? Because you add more water, and then some region will merge together. Okay, and if you go up and up, you can see maybe B, E, and W will merge together. Okay, because you keep increasing the water level, and at some point, those regions will merge. So MSER is also used for detecting or recognize the blurry text. So you can do it maybe from 0 to 255, or you can put it upside down from 255 to 0. So you can see it from both ways. Okay, and in that case, for blurry text, it could be something quite useful for you. And I may have showed this to you before, right? So this is the Robot X competition, actually in Singapore, 2 years ago, 1.5 years ago. And the task is to detect the symbol on the placard. By that time, we just use MSER because the MSER is fast enough. So if you try to choose different algorithms, some are feasible for real-time application, some are not. And by that time, we use MSER. We try to detect black region and the white region. Okay, so you can think of that the water level for, if you put it up from 0 to 255, the black will show up first, right? So that you can get the location of that blob. So it's a blob is a 中文就有点像一坨一坨的东西. So you can get the blob, for example, the circle in the center, or maybe the cross on your left-hand side. And if you keep increasing your water level, maybe some of the shadow next to the symbol will merge to the something we actually want, right? And if you put it from 255 to 0, and the first thing you can see might be the whole placard, the white one. Okay, so in that case, we try to detect it in two ways: from detect the darker one, or detect the white one, more like the placard. And we also try to use the black one should be enclosed in the white one. And I think it worked pretty well. And I think in the final of the competition, many teams don't even try, because maybe that's too difficult. If you do try something else, that could be not that easy. Okay, and actually MSER, it can run very fast, and we figure out some way to make it work, some clever trick. Yeah. So I think maybe since we have maybe 2 teams or even 3 teams working on parking, right? So maybe this is maybe one of the way to do parking, maybe compared to ducking for the water case, right? And we actually have it just here. So, but this is just one thing. For example, we want to detect the blue region, right? And actually, it can be done very easily by MSER. And maybe you can just add a little something, maybe just try to estimate the color inside the region, for example. And you can actually detect that region pretty easily. Okay. So this is another case we want to show you guys how MSER is working in action, so that you may want to use MSER for detecting objects, or even detect a ducky. Object detection problem. Okay, and face is one of the very useful case in this general object detection problem. So for example, you have a picture over here and you want to localize all the faces in this image. What's your strategy here? Suppose you are a face detector, and how are you going to do it? Maybe you can have a template of face and you try to slide the template around the image. Okay, maybe that's one way to do. So let's try it. So we want to find all the faces here. Some of them may be hard, right? For example, the one, 1, 2, 3 from the left, that one might be hard because part of the face is not actually showing. So we want to detect if this is a face or this is not a face. Okay, and we have a template over here. Okay, and we try to slide it somehow. Is there any problem with this box? Is this a good strategy to do it? 可能会切到一半的吗？那假如说它 slide， 它有一个叫做 stride， 就是它 slide 的那个间隔。它假如说好啊，我现在不管我花多少时间，我一个一个慢慢的扫，这样子 OK 吗？总有一天让我扫到你，这样。还有上下嘛？那好 ，stride 有 x 跟 y， 我现在也是不管，就是我一个一个 pixel 慢慢扫。好，脸的大小吗？Size is very important. Yes. 好，所以so in this case, actually, usually people will use a multi-scale sliding window. Okay, and typically, they don't actually change the size of the box. They actually change the size of the image and put it into we call it the image pyramid. So suppose you have this image this big, and you can make it smaller, 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 and smaller. And in that case, you can have one size of the sliding window and slide over all those image pyramids. But yeah, so 但是 different 不同 size 的 box 也是其实也是有人这样做。好，那 typically 在那个 implementation 的时候会用 image pyramid。好，那还有没有什么？我要不要用长一点的 box？ 还是还好？就是它那个这个 box 的长跟宽，我需不需要特别的调整？好像还好，对不对？因为人的脸，可能有些人脸稍微圆一点，但是也不会差到太多嘛。你不用弄一个这么宽的脸去 scan 这样子。Okay, how about that? Suppose we are trying to use a multi-scale sliding window to find a car. In that case, do you need to? You need a different, maybe you need a different aspect ratio, right? And how about a pedestrian? Maybe you need another aspect ratio for the pedestrian, right? Okay, cool. So after we do the sliding window and we have multi-scale, so that we can make sure that we have, usually if we scan it in this way, you will have more than 50,000 windows. And you also need to evaluate each of them. This is a face or not, this is a face or not, this is a face or not, and do it for 50,000 times. Okay. We found some of the faces here. But, okay, but for some reason, the tree, for some nature randomness, it also looks like a face somehow. Yeah, and this is called the false detection or false alarm, false positive. Okay, and also some undesirable case is that maybe some people, when they try to protest, they want to hide their face, okay, somehow, so that they have a strategy to maybe just show half of the face, or maybe show the bottom side of the face. Okay, so we have two undesired cases, missed or false detection. Okay, so in this case, we actually have a confusion matrix. Okay, the confusion matrix, this is the true positive. This is what we want. And this is also the desired situation. It is not a face, and detector tell you it's not. That's good. But we have two cases, the false positive. So it's not a face, but the detector tell you it is. Or false negative, which is the missing case. Okay. So there are some face there, but the detector could not find it. Based on the number of true positive, true negative, false positive, and the missing case, we can calculate a measure for how accurate this detector is. Okay, and in two different ways. One is called precision, and the other is called recode. Based on the definition, the recode, when you have a high recode, that means you don't miss any cases. And high precision is that you have very few false positive. Okay, so yeah, this is a little bit, maybe you need to think about it, but we will just give you a very quick introduction for now. And this is actually what we used for in our code. And it's called Viola Jones face detection. This is a very famous method by Viola and Jones, two very successful scientists. The algorithm is probably embedded in your cell phone or in your camera everywhere. Okay, very widely used. And the good thing is that the detection is very fast, although the training is not that fast, but that's okay. And the key idea is that first, we detect some feature, and second, we compute integral image so that the feature could be computed in any location of the image very fast. And the third one is called the boost method. And the basic idea is that you have a classifier, and maybe the classifier is weak, but if you have several of them, the several weak classifier could combine, become a strong classifier. And the last part, cascade. So the classifier is more like in a sequence. So you try to test one of the feature, and if it passes, you will go to the next one and reject the others. So that suppose you have 50,000 bounding blocks to evaluate. You don't need to go through every single step. You just need to check the first feature, and if it fails, just get rid of it and try the next one. Okay, so this will also speed up the detection. This is well, it's pretty hard to pronounce, maybe hard-like features. Maybe, I don't know if I pronounce this correctly. And the basic idea is that the feature look like something like those, some rectangles. And you can see, suppose we have a rectangle here, that could be something like dark, bright, and dark, right? And let's take a look at those features. Maybe some of the features will represent edges, some of them for line, or some of them center around, maybe some, maybe a corner or maybe a dot. Okay. And you can see that actually this man is Bill Freeman. He's now a professor in MIT. The interesting thing is that you can see, for example, the dark, bright, and dark. It will look like something like this, right? And dark and bright, it will look something like this. Okay, when we see those features, and maybe you will think that if I just block this region, those features, the hard-like features, may still find my eyes, right? And in that case, maybe this won't be good enough to fool a face detector like this. Okay. Okay, so those are during the training progress, the features could be learned from the example, and you can see something like this, right? The bright, dark, bright, or like this. They are pretty strong features for face. And the second part of the detector will be how to compute those features and compute the feature very quickly. Okay, so this algorithm also introduced a method called the integral image. Okay, the integral image is try to sum up the value from the top left corner. The best part is that suppose I want to compute the value of the features in a rectangle. I can just do A plus D minus B and minus C. Okay, and I can compute the sum of the blue area. Okay, I just use only 3 operations, and you can compute the sum of this rectangle. So in that case, it is great for the hard-like feature because all the features are some combination of the rectangles. Okay, and about the boost. So for each feature, maybe some of the features are more important than others. Suppose you only have one feature. Typically, it will not give you a good result. Okay, and if you can combine multiple of them, and multiple weak classifier can give you a better result. Okay, so this is a basic idea for the ADA boost. Okay, so you can see we have feature 1, 2, and 3, for example, and we have a weight for alpha 1, alpha 2, etc. And we can combine those different features and become a strong classifier. Okay, so the last part of the face detector is to use the cascade mechanism. So just like what we talked about, you don't need to check every single feature for a candidate for a region proposal. Suppose it cannot pass the first check, then we don't need to send it to the second one. Okay, and in that case, we can speed up the process very in a great level. Testing image for the Viola Viola Jones face detector. Some other test image.